Hello, everybody. Welcome to Thursday, October 9th's lecture on Chapter 5, the gaseous state. So, a lot of chemistry can be done in the gaseous state. This is actually specifically what UC Irvine is known for, is their atmospheric chemistry, which deals a lot with the gaseous state. So, if you were to go into chemistry, then that would be one of the options for you, is learning about how the air works, learning about how different gases can be used and stuff. So this is rather important. I should let you know that my throat is pretty sore, so you might hear me clearing my throat. I will try to keep it to a minimum, but that might be the case. Okay, so let's begin. So first, let's talk about what gases are. Gases differ from liquids and solids in that they are compressible, where you can compress liquids and solids, but to compress gases is much more easy and much more commonly done. And they are all related, all of their values are related to the pressure, volume, temperature, and amount of the gas that you have. And so we are going to abbreviate each of these as such. We have P, I'll make it a little bigger. We have P for pressure, V for volume, we have T for temperature, and amount is going to be in moles, so that is going to be abbreviated N. We abbreviate moles as N. So PV, T, N, and PV, T, and N. Okay, so when we're talking about pressure, this is how we're going to be calculating it. And we can do this with SI units. So if we're talking about pressure, let's say that we have a surface and we have some kind of thing sitting on it. Let's make it a, I don't know, some sort of shape like this. The mass has some sort of, or the object has some sort of mass that is going to be in kilograms or grams. And we're going to use grams for now. Well, we'll use kilograms because that's what it's measured in. Kilograms, and then the area that it makes contact with is going to be in square meters. But also, this meters per second squared comes up from acceleration. So acceleration is measured in meters times second, is measured in meters per second squared. And so to get to mass, you are going to use the value of a Newton, which is a kilogram meter per second squared. We'll do some rearranging of the equation. And really what's important is that we note that acceleration and mass are related to one another. In that pressure is going to be the product of how heavy something is over how fast it is accelerating, or something along those lines. Oh my gosh. Okay, so moving forward, we should take a second to look at these. So the units for pascals, these are going to be, each of these are different types of pressure. These are different ways to calculate pressure, or units to use our pressure values with. We have pascals, atmospheres, milligrams of mercury, and torr, and bar. So pascals have the units PA, or kilograms per meter second squared. Atmospheres have the units ATM, which is equal to 1.01 times 10, or 1.01 times 10 to the 5th pascals, which is about 101 kilopascals. So likely, if we're measuring something, we're going to measure it in kilopascals, atmospheres. There's also millimeters of mercury. So we'll get into why it's called millimeters of mercury in just a moment. But this is the same value as torr. So if you see 760 torr, that is equal to 760 millimeters of mercury. Those are the same thing. And same as if you had 1 torr, it would be 1 millimeter of mercury. So they're on the same scale and they have the same units. So I'll say that that is also equal to 760 torr. You have the bar, which is about the same as an atmosphere, just about the same as an atmosphere. As you can see, though, you have these units up here, 1.01325, and you have 1.01325. So there is a relationship in that 1 bar is going to be 1.01 times... it's going to... there is a relationship between these two numbers in that the only difference is that you have this 10 to the 5th present right there. Okay. Okay, so there are 2 ways that we usually measure pressure. Pressure is measured as a barometer, or with a barometer, which measures the atmospheric pressure. So when you're listening to like the radio or you're watching the news or something and they talk about the atmospheric pressure, they're talking about they use a barometer to tell you that. And this is how they can predict whether or not there is going to be a storm coming or the likelihood of a storm coming based on pressure differences in the atmosphere. A manometer is a device that you use to determine the amount of pressure of a gas or liquid in a closed vessel. So let's say that you had a flask over here, ignore my cat, and it's hooked up to a manometer. And I'll show you what that looks like. Please ignore my cat. She's trying to get to those hair bands that I offer you, and they are closed in my backpack, and so she's trying to sneak in there at the moment. Maybe I'll share a picture of her at some point trying to do that. She absolutely loves them. Okay, and let's say that we have in the middle of this middle part is called a manometer. We have mercury. And so if there is equal pressure on both sides, Opal, if we have equal pressure on both sides, we have Hg in the middle, we will have no difference in the height of the mercury in here. So equal pressure on both sides is going to make both of these heights of this mercury be exactly the same. If, however, we have much more pressure on one side than we do on the other, and just a little bit of pressure on this side, then we get something that's going to look more like this, where we have an unequal amount of pressure being distributed. And so on one side, we will get a much lower value, and on the other side, we will get a much higher value. And reading the millimeters of the millimeters that this mercury has traveled will tell us information about the amount of pressure pushing on one side versus the other of this manometer. So that's kind of how a manometer works. And we're going to talk more about, well, we'll talk in just a second about how to use them. So just to be clear, we'll say that this is measured in millimeters. Okay, we can use other units to measure pressure as well as millimeters of mercury. So there's torr and millimeters of mercury. And the relationship between pressure, you can also use things like millimeters of water or inches of water. That is often a used pressure. in the United States, but generally atmospheres and millimeters of mercury or torr are what we use in science because they are clean numbers. There's also PSI, that's another one, pounds per square inch. That's something you'd see on a tire. Okay, so the relationship between pressure and the height of a liquid when we're talking about a barometer is going to be this: P, G, D, and H. P equals G, D, H, where G is the constant acceleration of gravity, which we've talked about the acceleration before. It is the number of meters per second squared, the amount that the meters per second is increasing. D is the density of the liquid in your manometer, and height is going to be however high your liquid is in that manometer. And so we can see here that, just for example, if we have a 1 over here, and we have a 1 for G times a 1 for D times a 1 for H, then all of these numbers are going to be the same. These are all going to be proportional to one another. If we increase one of the numbers, so let's say we increase height to 2, then that means that pressure is going to be directly proportional to that. 1 changes to 2, and so the pressure is also going to double. In order to get it back, so that means that pressure is directly proportional to G, D, and H. So in order to get it back down to 1, though, while making H be the same, then we have to change one of the other numbers, either G or D, and we cannot double it. If we double it, let's say that we double it here, then we're going to get a doubled number on this side. We'll get a 4. And so that's not allowed. So instead, what we can do to get that number down is halve it, cut it in half. So in order to get that number down, we have 1 times 2, which is 2, times 1 half, which is going to be 2 times 1 half is 2 divided by 2, which is equal to 1. So we can change this number to 1. So that means that G, D, and H are inversely proportional to one another. Inversely proportional. So that means that if you increase a G and or a D or an H, then to keep the same pressure, you have to do the opposite to one of the others, G, D, or H. Okay. And so we can now continue to the next part, and we'll give you a I'll give you a second. You can go ahead and read this. I need to drink a little bit of water and start a timer real quick. Okay, so let's say that we have two different setups, like the one below. In one of the barometers, we're going to put mercury, and in the other one, we're going to have just water. And so we want to know which of them is going to have a higher column of liquid, the one with water or the one with mercury. And so to know that, we need to know what the densities are. Down here, we have a density of mercury, which it's very heavy. It's a metal that is a liquid, but it's very heavy. So 13.6 grams per milliliter. For water, we have 1 gram per milliliter, 1.00. And so if we go back here, we can see, since height and density are inversely proportional, then the greater the height, the lower the density to maintain pressure. So, if we look at this, if pressure is a constant, then and density is higher, if height is higher, that means density is lower. If density is lower for a substance, then it will be easier for that substance to resist gravity and it will be able to go higher. And so it's going to go higher because up here we have a vacuum. It's going to be sucking, it's basically going to be trying to fill in that vacuum, whereas the pressure outside is going to be pushing down on the liquid, forcing it up into there. Okay. And so, as a kind of test, I'm going to block out this. Go ahead and close your eyes for a second while I do this because I don't want you to see the answer. But I'll give you a second. Go ahead and read the problem. We're going to be doing something very similar with benzene and with bromine. Benzene is this clear fluid on the left where we have benzene, which is also C6H6. It is an organic molecule because it has carbon bound to hydrogen. And we have bromine on the other side, Br2. Okay, I'll pause here. You can go ahead and try to use this equation to see how this might work for the same kind of setup. Okay, and so let's go through it. We have, the question is asking, if we do the same setup with bromine, which has a density of 3,100 kilograms per meters cubed, and benzene, which has 877 kilograms per meters cubed, instead of water and mercury, if both liquids reach 101 kilopascals of pressure in the tube, what are the heights? And so we can take this equation and rearrange it. So we have P, we'll divide both sides by G and D, and we have G, D on that side, and then over here we have this equal to H. And so we want to find what those are. And so all we need to do is take the pressure, which is 101, the the gravity constant, the acceleration of gravity, and density, and we will be able to find out what that height is. So we'll take that, divide it by those numbers multiplied, and we get 0.33 meters for bromine, which is a lower height than for benzene, which is less dense at 0.0117 meters. And so this again proves that the less dense of the thing that you have, the higher it will go in a barometer. Okay, so this is the real thing that we're going to be using. So that last one is how to measure a barometer, but for the empirical gas laws, it's a little bit different. And so the empirical gas laws are talking about how we are going to address gases. So all gases behave quite simply with respect to temperature, pressure, volume, and molar amount. That's going to be T, P, V, and N, just like on slide, I think it was 2. And so by holding these properties constant, we can show how there's a simple relationship between the other two properties. And the studies that led to this occurred in the mid-17th century, so these are very old laws. And so back then, and they still do this today, but back then, they really like to name laws after themselves. And so we're going to go through a lot of, whoever discovered it loves to name the law after themselves. And so we're going to see a few different laws that are going to relate to gases and stuff like that. But before we get to those, let's go over the rules of these gas laws. So if we're talking about temperature, temperature is going to be measured always in Kelvin. So that is something that's very important. And remember, in order to get from Celsius to Kelvin, Kelvin, you just add 273. That's it. 0.15 if you're being more specific, if you need more significant figures. And so I discussed this before, but N is going to be what we're referring to as the number of moles. So we'll be talking about the number of moles of gas quite a bit. We're also going to come up with something a little bit later, but this probably in the next video, but 22.7 liters is going to be the volume of 1 mole of gas. It doesn't matter what kind of gas you have. 22.7 liters is always going to be what the volume of 1 mole of gas is. Okay. And so we can continue and go with the P. P is going to be for pressure, and the units are going to change wildly for this. As I showed you before, on this slide right here, we have many different ways to talk about the units of pressure. We have pascals, kilopascals, which are just 1,000 pascals, atmospheres, milligrams of mercury, and torr and bar. And so it doesn't, we have lots. We have ATM, all lowercase. We have kPa, PA. We have torr. We have millimeters of mercury. Those are going to be the most common ones. So those are probably what I would use if I was testing you on this. For volume, the units also can change because of R. We can go anywhere from meters cubed to centimeters cubed to decimeters cubed to milliliters. Keep in mind, 1 centimeter cubed is equal to 1 milliliter. Those are the same unit, they just look different. And then we have the R, the gas constant. So this is the one that is going to be affecting volume, and it's going to be affecting pressure. And so either one that you, depending on the gas constant that you pick, this is what's going to be what determines what your units are in the end. You can always convert out of those units, but that's what it's going to be to begin with. Okay, so let's talk about the ideal gas law. So this is the ideal gas law, and I have this slide in here twice to remind you of what the different things are, but this is actually only a few of the different possible gas law values of R that we can use. But this is the ideal gas right here. PV equals nRT. And when I was in high school, my teacher told me, his name was Dr. Moody, my teacher told me, the way that you can remember this is just say the word pervert. It doesn't really look like the word pervert, but it's close enough. So PV equals nRT, pervert. And so it's gonna come up quite a bit. But we have pressure and volume next to each other. Then N, the number of moles, R is our gas constant, and T is our temperature. The molar gas constant is the constant of proportionality. And so often the molar gas constant is going to have a ton of units at the end. We have liter atmospheres divided by Kelvin moles. We have joules for Kelvin moles, which is the same as kilograms meters squared divided by seconds squared times Kelvin times mole. All of these are really just to be able to cancel out all of those units. The units change, the numbers change, not by too much, but they do change. And you might also notice that 3 of these are the exact same number. And so that is something that you're going to want to keep in mind as well. Sometimes this is going to be the most often used one right here, 8.3145. But there is also this one up here, liters atmosphere per mole Kelvin. Atmospheres are a lot easier to deal with, and so the easy problems that I give you are probably going to have atmospheres and use this constant for R. The harder problems I give you are probably going to have joules per Kelvin mole, which is the one below it, because those are a little bit more complex. And the hardest ones may have calories. It depends on how evil I'm feeling that day. Okay. So, the thing about this ideal gas law is it's called the ideal gas law for a reason. The ideal gas is the idea that gases are all going to be behaving the same. And so it doesn't matter what kind of gas you have, they're going to behave as a ideal gas. Some of them are going to be denser and heavier and stuff like that, but they're all going to behave in similar ways. And so when we get into these next parts, we'll explore some of the ways that all of these gases behave. And so next we have the first example of one of the 17th or 18th century people describing the law that they discovered. And so Boyle's law is the volume of a sample of a gas constant at temperature varies inversely with the applied pressure. And so volume is inversely proportional. That's what this means. Inversely proportional. Or I guess it would be proportional. That would just be proportional. It's proportional because, and not inversely proportional because we have 1 divided by, this is the inverse part. The 1 over P means that that is in the inverse. Volume is proportional to the inverse of pressure. And so when we put that into an equation, we actually put those on the same side for the same reason that when we had P equals G dH, remember all of these were inversely proportional. So inversely proportional on the right-hand side. And so these two values are going to be inversely proportional. But just like we did M1V1 equals M2V2, these are going to be very, very similar in that regard. So for dilutions and for the changing of pressure and volume together, the relationship of pressure and volume together, we're going to see something very similar. And so in the same way that we were able to get M1V1 equals M2V2 by rearranging the idea of molarity, where molarity is equal to moles over liters, I guess we can use N for moles, so N divided by L. And we set 2 of these equal to each other once we rearrange it to get M1V1 equals M2V2. I'll even change that to V so that it's clear what it is. We're going to do the same with the ideal gas constant and these values. So also keep in mind, I was raised to write P1 V1 equals P2 V2. Either way is fine. You can write an I or an F or I and F or 1 and 2. I wouldn't mix them up, but that's what you can do. Okay, so I'll show you how to do this one, and then for the next one, when we have to rearrange some stuff, I will show you how, I will let you do it on your own. But basically, this is how it works. So what we're saying is that P and V are our variables. N, R, and T are our constants. So if let's say that we have a container, initially we have some pressure, we have P1, and we have some volume. Now, if we make that box smaller, let's say that there's some, I'll put some gas molecules in there. Let's say that it gets smaller. We have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. We change the volume. That is going to make a different pressure, but the number of moles stays the same. R is already a constant, so that doesn't change. And we are going to keep the temperature the same. This is something that we are going to keep the temperature the same as. So we have now on the other side a different pressure, P2 and V2. And so we've changed the volume, which may change the pressure. The volume has gone down, which may change the pressure. But all of these are the same. So we can say that P1 V1 equals nRT, and P2 V2 equals nRT. And so P1 and V1 are different from P2 and V2, but nRT are the same. And so we can say P1 V1 equals nRT, which is equal to P2 V2. And because of this, we can just get rid of nRT. So P1 V1 equals P2 V2. There you go. And so as the volume of the box is going to shrink, the pressure of the box is going to change as well, and it's going to be inversely proportional. But this is how we would show that. All the other units are going to be staying exactly the same. These are all constants, so they're not going to be changing. But P and V are variables, so we have to determine them as P1 and V1 and P2 and V2. And so this is how we take the ideal gas law and transform it into Boyle's law. It's by doing this. This can be done for any of the named laws. So that's why I have not committed to memory any of the names of the laws coupled with what the law is. I know them a little bit by name, but that's it. And that's really just because I don't need to. As long as I know it's being held constant and I know it's being changed, then I can make my own law, and that's fine. Okay. Okay, so this is an example of Boyle's law, though. So at normal atmospheric pressure, the volume of the gas is 100 milliliters. When pressure is doubled, the volume is halved. When pressure is tripled, the volume is decreased. So specifically, we're talking about the volume right here, this enclosed gas right here. If we increase the pressure by doubling it, specifically by adding more mercury, then we will decrease the amount of volume in the gas. So that means that doubled pressure equals halved gas. Same thing, if we triple the pressure, we will make the enclosed gas be a third of the volume that it was before. So another way to look at this is that when we have a 1 gram sample of O2, we have a 1 gram sample of O2 gas at 0 degrees Celsius. It's placed in a container, so this could be like the piston of a car. At a pressure of 0.5 atmospheres, it occupies 1.40 liters. Now, when we compress that by quite a bit, if we double the amount of pressure from 0.5 atmospheres to 1 atmosphere, then the amount of volume is going to reduce as well, because they are inversely is going to if we double the pressure, it's going to reduce the atmosphere because they are inversely proportional. And so that's how we get them on the same side of the equation. PV equals PV. We have a 1, 1, 2, 2. Inversely proportional. If one goes up, the other goes down. Okay. Plot of volume versus pressure as an example. So this is one thing that does occur, is that if you take the volume of pressure and plot it against, the amount of pressure, and you plot it against the volume, you will see a curve like this, where it is not a linear curve. It is at a slope. However, if you give the inverse of one of the values, so you take 1 over whatever your volume is, that's how you'd get a straight line, because it is going to be inversely proportional. Okay, so to apply this, I apologize for the break. I had to cough real quick. To apply it to Boyle's law to an actual problem, this is what it might look like. So, a volume of air occupying 12.0 decimeters cubed at 98.9 kilopascals is compressed to a pressure of 119.0 kilopascals. The temperature is going to remain constant. And so we already know from the solving that we did that PI VI is going to be equal to PF VF, or P1 V1 equals P2 V2. Either way is fine. And so what what we need to do is we need to define what these are. So let's just gather all the information that you know first. So VI is going to be your initial volume. So our initial volume is 12.0 decimeters cubed. And you might notice that we don't necessarily need to match up all the units right away, because the units are going to be canceled out for the most part, right? We're going to, whatever pressure unit we have here is going to be divided by that pressure unit, so we can cancel those out. Whatever volume unit we have here is going to be the same volume unit we have there, so there's no problem there. But anyway, we have V1 being 12 decimeters, and our first pressure is 98.9 kilopascals. And then we do a compression. So if we have like a piston in a container with gas in here, we're going to do a compression in the next step where we have much less space for our gas, and we'll compress it down there. So the volume changes, and we want to know what that new volume is, because we do know what the new pressure is already. So the PF is our final pressure, and that is going to be 119. So I'll just put that here. Now, in order to get this to look like that, all we have to do is divide by PF. PF is what we will divide by. And then these are going to cancel out. All we'll be left with is this right there, and we just flip it. So we put the VF on the left-hand side to find what that looks like. Now, once we have this information, we can start plugging things in. So we know our VI is going to be 12.0. We know that our PI is going to be 98.9. We know that our PF is going to be 119.0. And that's all we do. We end up with the answer of 9.97 dm3. Again, those units are going to cancel out. Okay, so I'll give you a second to give this next one a shot. Go ahead and give it a try, and let's see what happens. I'm also going to go like this, and then I will reveal the answer. It was already there for a second, so if you wanted, you can just scroll back, but I'll reveal the answer in just a second. Let's see how we get to this point. Okay, so a volume of air occupying 15.6 milliliters, notice that that's different than decimeters cubed, at 1.36 atmospheres, ATM is atmospheres, is decompressed, which means that pressure was released. Okay, well, it's... Oh, no, that's correct. It's going to be decompressed to a pressure of 0.604 atmospheres, and the temperature is going to remain constant. We want to know what the new volume is going to be. And so we'll do the exact same thing. So all we need to do is recognize where we get our VI from. Our VI comes from our initial pressure. Our PI comes from our our VI comes from our initial volume, our PI comes from our initial pressure, our PF comes from our final pressure, and we'll just plug those values in. From this, we are able to get VF equals PI VI over PF. So we'll plug those in. We have 15.6 times 1.30 for our volume and then our pressure. Doesn't matter what order you put them in, it's a multiplication. And 0.604 for our final pressure. We do this math and we end up with our answer of this right here, 35.1 milliliters. 35.1 milliliters. Okay, let's keep going. So Charles' law is another example of how you can rearrange the equation and keep something the same. So the volume of a sample of gas at a constant pressure, now we're keeping pressure constant instead of temperature, and moles, is going to be directly proportional to the absolute temperature K. And so in equation form, we have the volume over temperature is going to be equal to our constant, which we will define on the next page. And so VI over TI equals VF over TF. And let's take a look. So I'm going to pause again. Go ahead and try to solve this on your own. See how you can take PV equals nRT, set it equal to some number. Feel free to scroll back in the video if you would like to see how I did the first one for Boyle's law. And then see how these things can become equal. And then I will help you solve it. Okay, so we have PV equals nRT. Now, what are we keeping constant in order to get V and T on the same side? So V is here, T is here. I will go ahead and circle those. We have V and we have T. Everything else needs to be constant. So the first thing I'm going to do is divide by T. T will be divided, we'll divide by T, divide by T. We want everything that is going to be a variable on one side and everything that's constant on the other. So we end up with PV over T equals NR. And now pressure is going to be constant as well, so we'll divide by P. Divide by P, and we get V over T equals R over NR. NR over P. And so all of these are constants. So what we can do is we can say that this is V1 and T1 or VI and TI. And we can also say that these are going to remain constant no matter what we do to it. So that means that V2 over T2 is also going to equal NR over P. These are going to be the same number, which means that that is also equal to VI over TI, which means that we have VI, or V1 over T1, VI over TI equals VF over TF, or V1 over T1 equals V2 over T2. Either one is fine. Okay. So for a demonstration of this, we can take a balloon. And so liquid nitrogen, this was a substance that I believe I used on your first exam, I think. Or maybe that was helium. But liquid nitrogen is a really, really, really cold liquid, right? When you think of nitrogen, you think of a gas because nitrogen is in the air. It makes up quite a bit of the air. And so if you are to take a balloon full of room temperature air and put it into, freeze it basically, make it really, 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 really cold, then what you get is you get a shriveling of this balloon where the gas has gone down. It looks like the gas has basically disappeared. There's still some gas in there, but it looks like it's basically gone. And so when you place that balloon into there, you get it to freeze up like that. And then once you take it out, it's going to start to warm up again and expand. So it shows that the volume and the temperature are going to be inversely proportional. If we were to look at a graph of this, we could take each of these different gases and we could say that if we were to graph them, then depending on the temperature, the volume, or sorry, not inversely, directly proportional. The temperature and volume are going to go down directly toward one another. And they are going to stop right here, negative 273. Negative 273 is where 0 Kelvin would be. Of course, we cannot get all the way down to 0 Kelvin, so this is an extrapolation, but this is what is expected to happen. And also comparing the other graph that we looked at where we had 1 over volume, now we just have volume. So volume and temperature are going to be directly proportional rather than inversely proportional in order to get a straight line. We can see this again with this example where a 1 gram sample of O2 at 100 degrees Kelvin and 1 atmosphere of pressure is going to occupy 0.26 liters. When we double the temperature of the gas, we will also double the volume of the gas. So it goes from 0.26 liters, multiply that by 2, we get 0.52. When we have the same would happen if we were to double the volume, the temperature would rise as well. So for this problem, I use very similar numbers to before, but if we have a volume of air occupying 15.6 milliliters at 13.36 milliliters C, then we cool it to 2.604 C. All the other values all the other values remain constant. This is what we end up getting. So we want to know what our final volume is going to be once we cool this down. And we have our 15.60 starting volume, our 13.36 Celsius starting temperature, our 2.604 degrees Celsius ending temperature, and we don't know what our ending volume is. So we'll start with this equation and convert it. We want to isolate VF by itself, and so we will multiply by TF on both sides. So we get VI TF divided by TI equals VF. And so we can plug in those values. That's going to be 15.60 times, for our milliliters, our TF is 2.604 degrees Celsius. I won't put those in because I didn't prefer the other one. Actually, my mistake. We're not quite done. So first, before we continue, I noted on one of the earlier slides that if you have a temperature, then it must be converted to Kelvin before you are able to actually use it. And so that's what we're actually going to do first. We're going to take this temperature and convert it to Kelvin. So for Kelvin, all we have to do is add, when we're going from Celsius to Kelvin, is add 273. So 2.604 plus 273.15 plus 273.15. That's going to equal 239.754. And we have to do the same thing over here. So all we'll do is add 273.15, and that's going to be 13.36 plus 273.15. That gives us 286.51. So these are our new values in Kelvin. So our TI is now going to be that value, and this is what we'll plug in. So VI is still 15.60 13.6. We'll divide that, or multiply that by our TF, which is going to be 239.754. And then we will divide that by the TI, which was 286.51. And so, yeah, so when you're approaching these problems, it's very important to remember to convert to Kelvin, because Kelvin, you are going to get the wrong answer pretty much if you are going to not use Kelvin and you just stick with Celsius. And that is because of that zero issue where 0 Kelvin and 0 Celsius are not the same number. And so when we actually do this math, we end up getting 13.0, and actually it's 13.1 when we round for, oh, that's a 0 right there. So 13.05 milliliters. And let's see, is this what we got here? Not quite. And that is because I probably didn't do that with the correct values. And so it goes from 15.60 milliliters to 13.05 milliliters when you actually do this math correctly. Okay. So the combined gas law is not going to be one of the ones that is equal to it's not going to be the ones that's named after one of the people who invented it. This is just the combination of Charles' law and Boyle's law. And so we end up getting from PV equals nRT, PI VI over TI equals PF VF over TF. Okay, give this a shot. Okay, so I'm going to speed run this, but basically we have PV equals nRT. In the final equation, we have N and R being the only ones that don't show up, so that's what's going to be on the other side of the equation. PV, we're going to divide by T over T equals NR. We'll set that to 1, 1, and 1. That means that P1 V1 P2 V2 over T2 equals NR as well. So P1 V1 divided by T1 equals P2 V2 over T2. Okay, so for the first problem for this, the Dumas method, this is a actual analytical technique that you can determine the mass of something from what you are looking at. But we do not need to do all of this work to figure it out, because the only thing that we need to do is determine the volume of nitrogen. So the Dumas method is going to tell you things like the amount of nitrogen that you can get out of an organic compound. And so if we had 39.83 milligrams of caffeine, it's going to give 10.1 cubic centimeters of nitrogen. Remember that this is equal to 1 milliliter of nitrogen gas at 23 degrees. Eventually, we will have a whole lab on the Dumas method, so don't worry about it for now, but basically it's just a way to see what elements are present in a compound that you have. So at 10.1 milliliters or CM3 of nitrogen gas with 23 degrees Celsius and 746 millimeters of mercury, we want to determine the volume of nitrogen at 0 degrees. 0 degrees. And so we will start by writing out all of the different information we have. And actually, since the slides are already up, this is not a question that I wrote. I wrote the next one. But go ahead and try it out yourself. See if you can figure out exactly how to do this. And don't forget that you need to convert your temperatures into Kelvin before you use them. Okay, so let's try it. So our P1 is going to be whatever we start with. So our first pressure is given here in millimeters of mercury. That is going to be 746 millimeters of Hg. Our V1 is going to be our initial volume. That's going to be 10.1 cubic centimeters. Our T1 is 23 degrees Celsius, so T1 equals 23 degrees Celsius. If we add 273.15 to that, we end up getting 296.15. So 296.15 Kelvin out of that. And so we can keep going. Our P2 is equal to 760 millimeters of mercury. Our V2 is equal to, we don't know yet, that's what we're trying to find. And our T2 is equal to 0 degrees Celsius. So we add 273 to that, 0.15. We end up getting 273.15 Kelvin. Okay, and so our equation is going to be, if we look back before, what we wrote is P1V1 over T1 equals P2V2 over T2. P1V1 over T1 equals P2V2 over T2. And we can just start plugging things in. Our P1 is 746. Our V1 is 10.1. And we will divide that by our T1, which is 296.15. We need to get V2 all by itself, so we'll multiply it both sides by T2. And so the top value is going to be multiplied by T2, which is 273.15. And we also need to divide by P2 on both sides, so we can cancel these out. And we end up getting our P2 on the bottom, which is 760. Okay, and so we end up doing this math, and we should get 9.14 cubic centimeters. And so if we look at the answer, this is exactly correct. So T1 is going to be 23 plus 273. It gives us 296. For what I do, I tend to use the 0.15 as well so that you can have extra sig figs when you need them. For TF, you have 0 plus 273. Again, we get 273. We have our volume. We have our initial pressure, our final pressure. We don't know what our initial or final volume is. We have our initial temperature, our final temperature, and we're going to set up the equation just like I did before, ending up with 9.14 cubic centimeters. Okay, so so for this problem, we're going to do the exact same thing, and there's a couple things that we need to watch out for here. So if we have a volume of air occupying 15.6 milliliters at 1.36 degrees Celsius and 21.1 millimeters of mercury, this is going to be our V1, this is going to be our T1, and this is going to be our P1. And then we have a temperature, another temperature. We're going to cool this to a T2 of 0.604 and a volume of V2 of 2.30 centimeters cubed. All other values remain constant. Determine the new pressure in kilopascals. So the first thing you should notice is that kilopascals is not going to be one of the units that we are in. So this is another unit of pressure. We have currently millimeters of mercury. So the first thing that we want to do is we want to convert this to millimeters of mercury. It's going to save us in the long run if we do that. Literally, I had to restart the video because I forgot to do that. So we have 21.1 millimeters of mercury for every 760 millimeters of mercury. And you can get this value from that chart over there. I will put this, if there's an exam on this, I will put these conversions on a worksheet for you, or on a equation sheet, so you have them all. Convert that to 101 kilopascals. It's about 101. It's a little bit different, but that'll be fine. So 101 kilopascals. The number we end up getting out of here is going to be 2.80 kPa. Now, the other thing you should notice is that we have 1.36, and that is going to be in Celsius. So what we do is we add 273 to that to get it to Kelvin, because we cannot do these equations if they are not in the correct units. So Kelvin, we have, we're going to add 273 to that. We end up getting 274.51. And we'll do the same for the TF. So TF is going to be 273.754. And it's okay that those sig figs are a little bit long. We're going to trim them down at the end. And so now we have it in kilopascals. Everything should work out, but we need to rearrange this equation so that we can have the correct units. So what we'll do, I'll zoom in here. We're going to multiply both sides by TF in order to cross that out. Our goal is to find out what the final pressure is. And so we're going to multiply that we're going to try to isolate that on one side. So this is going to end up with a TF on that side, multiplied, and then we'll divide both sides by VF. So divided by VF, we're going to get rid of that. And so all we're left with is PF. So VF on this side, TF over VF is going to give us just the equation that we're looking for with only that at the end. I'll rewrite it right here. And so we have TF, I'll even go a little bit smaller so it's easier to see. We have our final equation that we're going to plug everything into is going to be TF times PI times VI divided by VF times TI, which equals PF. And so we'll plug in the values. Our VI is going to remain the same. Now, you might notice we have milliliters on one side, cubic centimeters on the other. I do not have to convert these because 1 milliliter is equal to 1 cubic centimeter. And so I can just use those values. So TF we determined was 273.754. So that's 273.754 times PI, which is now in kilopascals, 2.80 times VI, which is 15.6. And we'll divide that by our VF times TI. So TI is 274.51, 274.51, and our VF is 2.30, so 2.30. We'll multiply those together in the middle, and that is how we are going to get the value. So once we do all this math, we're going to end up, this is incorrect because we were looking for the final pressure, I believe, correct? Determine the new pressure. So our PF is going to be equal to all of this math, which will give us 18.9 kilopascals. And so our new pressure is going to be 18.9 kilopascals. Okay. And so this is another workspace that you could use if you'd like. These are going to be the conversions that are going to be useful for you to do it. I recommend trying to do this one on your own without any help. See if you can get that equation. Honestly, if you can do this equation starting from PV equals nRT, and you can solve all of this information here, then you can likely do every single, this should be an F, you can likely do every single problem that you're going to need to, okay? And this is going to be the answer. Go ahead and check your work at the end. I'll give you a second if you need to pause the video. Okay. And so I'm actually going to end it here. This is where I plan to end it during class today. And then I will upload another video when I can. Thanks so much. Bye-bye.